Okay, I'm going to go through the reaction of alkali metals with water. Now, there's plenty of resources available in the video links section already on this, so I'm going to try not to spend too much time on it. I just want to supplement what's already there with some equations and comments and a couple more videos. Reaction of alkali metals with water. Okay, so I picked a typical IB exam question and I thought we'd go through it. And I want to show you some videos too, so I'm just going to have a look at these ones. Now this is me doing this experiment. So I've got a piece of sodium, little tiny piece in a pair of tweezers, and I'm just going to knock it into this petri dish full of a little bit of water. It's also got some phenolphthalein added to it. That's a pH indicator that is colourless in acidic solution and pink in basic solution. So here we go, knock it in. First thing you'll notice, I suppose, is the immediate pink colour, which indicates that we're making a base. So if I'm adding sodium and there's water involved, the base is probably sodium hydroxide. You can see the sodium, it's moving around on the surface. Now that's interesting, why is it doing that? It's making a gas. It's hard to see. You can't see any bubbles really, but the gas is moving, propelling it around. That's also one reason why it's floating. Another reason that it's floating is because it's so light, but it's also producing lots and lots and lots of gas bubbles, which help it to float. And it also helps that it's hydrogen gas bubbles. Hydrogen's really, really, really light. So if you're trying to remember the two products, remember this video. Remember that the solution went pink. That must mean it's a base. It's a hydroxide, sodium hydroxide. Why is it floating around on the surface? Why is it moving so much? Well, it's making a gas. What gas? A really light gas? Hydrogen. Hydrogen is also what makes them flame, if you happen to get a flaming one. Here we go. Same deal. Sometimes you get a flame, sometimes you don't. When you add sodium to water. There we go. Nice flame. Why do you get a flame? What is that? The sodium's not burning. The water's not burning. What's burning? What are we igniting? The hydrogen gas. That's another reason you know that there's hydrogen gas, because it's flammable. Why did this one make hydrogen gas that ignited and the other one didn't? The other one just made hydrogen gas. I think, if I had to guess, and I don't really know, this one sticks to the side. You're generating that hydrogen in a specific place. It doesn't get away quick enough, so it ignites. And the heat that is generated by the exothermic reaction of sodium with water ignites the hydrogen that's sort of collecting in that one location. Okay, and that's why we get a flame for this one, but not in the other one necessarily. Okay, so I'm going to flick back to our slide. State the equation for the reaction of sodium metal with water. I know that I've got some sodium metal. You can even put state symbols in if you like. It's a solid, or is it? That's another thing. When I added the sodium to water in those videos, it turned into a little ball. Solids don't change shape, do they? That's odd. It's odd that it should change shape, because it is very, very clearly, and I can't help it, I'm just going to switch back. It is very, very clearly not a ball in that very first slide, right? So what we're looking at here is a little chunk of sodium, a piece, a rectangle, if you like. Then you put it into the water, and it goes from being a rectangle, and very, very quickly it goes to being a ball, a sphere. It's not actually a solid. It doesn't stay a solid. That reaction is so exothermic that it gives enough energy for that sodium to melt. This one, it's a bit more obvious, because that one is a bit... I tried very hard to get spherical pieces of sodium, so I cut that one so it was a nice long rectangle, adding that to water, and immediately it turns into a ball and goes around on the surface. The shape minimizes the contact with the water. So actually, technically, it's not really a solid. It's actually, on the outside at least, it's a liquid. Molten sodium, it has melted. The melting point of sodium is only slightly less than 100, I think, off the top of my head. So it doesn't actually really take a whole lot of energy to get it to melt. And it is quite an exothermic reaction, of course, if it is hot enough to make hydrogen ignite. Right, so it was a bit misleading to write solid. I might leave the state symbol out, just because I don't want to do that. But I mean, sodium at its under ordinary conditions is a solid. So generally, when you see it written, it does say solid. Water is my other reactant, and I know my two products are sodium hydroxide because I remember it made a basic solution, and I made hydrogen gas, and that can be ignited. Oh, I can't help myself. I really want to put state symbols in. That sodium hydroxide, of course, it's dissolved in the water. It doesn't precipitate out of solution. Okay, so it is definitely aqueous. It has dissolved in that water that is there. The sodium doesn't dissolve, and look, I really don't mind whether you want to use an S for solid or an L for liquid for the sodium. Either would be correct according to the IB. Yeah, so the sodium doesn't dissolve, it reacts. It's definitely not dissolving. It is definitely not. It is definitely undergoing a chemical reaction that is different than dissolving. So it reacts with the water, produces a solution of sodium hydroxide and hydrogen. Of course, we can't forget to balance that. I've got 2 hydrogens over here for my H2 gas, and 1 there. So there's 3 on the right-hand side. So if I just sort of go, okay, well, I'm going to need to multiply that by 2 so that I can have 4. And then everything else is balanced except the sodium, which needs a 2 as well. 2 changes that could be observed during the reaction. Oh my goodness, you could write anything. But look, what's going to be on the mark scheme? That's good. That's a really good thing to worry about. You might see fizzing or bubbles. You're seeing a gas produced, basically. That's something that they really, really want you to recognise. Also, it's an exothermic reaction. So you're perhaps observing that the solution became warm. Maybe you stuck a thermometer in there, and you noticed that the temperature on the thermometer went up. Maybe you noticed that there was a flame. And they do often ask you about sodium and potassium so that you can write flame. They're all very similar reactions, the alkali metals, but potassium and sodium are the more reactive ones. Hopefully you've watched the video with all of the different alkali metals reacting with water. And you know that potassium is very, very quick and you're basically guaranteed a flame. Sodium, it's a bit slower and you're not guaranteed a flame. But you can write that. You can write flame or heat on your IB mark scheme. You could see an enormous amount of other things. If you've added phenolphthalein, you could observe that the solution was whatever the basic colour of your indicator was. So for me it was pink. And that's if you add an indicator. There's all sorts of other things that you could write that I wouldn't necessarily recommend. You could write that the sodium melts and forms a ball. That's fine. I mean, you could write that. It's probably not on the mark scheme. You could write that it changed shape as a result. Again, probably not on the mark scheme. You could write that it skidded around on the surface. And again, probably not on the mark scheme. So there's probably things that you can write and things that you're not necessarily going to write. Relative rates, well, we're looking at size, basically. As the alkali metals get bigger, the ionization energy gets smaller. So the energy that you need to put in to get these reactions to go is actually less. Conversely, they have in a related way, they have a faster rate of reaction. So they react much more quickly the bigger they are. So the bigger those metal ions are, and I suppose it's the ions we're talking about. Oh, sorry, no, it's not. That's the products. So the bigger those metals are, the quicker that they react. You'll notice on the videos, the alkali metals videos, that cesium is an incredibly violent explosion, and then rubidium's an explosion, potassium's a flame, and a bit of an explosion. So potassium, in this question anyway, will react the fastest. Sodium will be a little bit slower than that, and the lithium will be the slowest. So sodium, you would say, is intermediate between the two. I think it's just a 1 mark question. In all honesty, you could write potassium is faster than sodium is faster than lithium. That's it, and that's the reactions of your alkali metals with water.